Imagine this. Traveller, you've arrived at the exact moment the universe intended. Two lights, one slender and green, the other wide and ghostly, are racing toward the sun from opposite directions, converging in a 1 in 20,000 chance alignment. One of them, 3I Atlas. The largest interstellar object ever detected slips past the orbit of Mars like a silent needle of light. The other, Swan R2, brightens far too quickly, as if made of something our solar system has never seen. And now both are sinking into the sun's glare together, disappearing at the very moment their secrets might matter most. What are the odds? And what if the timing isn't accidental at all? Stay with me, listener. Let's drift a little deeper. October 2025 presents one of the most unusual astronomical alignments in modern observation. Two unrelated cosmic objects originating from entirely different regions of space are converging toward the sun within the same narrow window of time. This coincidence is not simply aesthetically striking. It challenges long-held assumptions about the statistical distribution of near-solar encounters and forces a reconsideration of how we interpret transient phenomena in the inner solar system. The first of these objects, designated 3I Atlas, was identified on July 1, 2025 by the Atlas Survey Telescope in Chile. Initial astrometric measurements revealed a hyperbolic trajectory confirming its interstellar origin. With an eccentricity exceeding 6.1 and an incoming vector from the direction of the galactic centre, 3I Atlas became only the third confirmed interstellar visitor ever detected, following Oumuamua in 2017 and 2I Borisov in 2019. Unlike those earlier visitors, however, 3I Atlas displayed detectable activity at distances far beyond what thermal models typically predict for natural comets. Early imaging indicated a developing coma at more than 6 astronomical units from the Sun, a region where most objects remain cold and inert. Several weeks later, a second object entered the observational frame. Comet C2025 R2 Swan emerged from solar conjunction already active, already bright and already displaying a substantial tail. Its rapid brightening suggested a volatile composition not fully consistent with classical Oort cloud comets. The timing of this reappearance, occurring only months after the discovery of 3I Atlas, established the foundation for what would soon be recognised as an extremely rare dual approach toward the Sun. Statistically, the near-simultaneous inward migration of two objects from unrelated origins is notable. Orbital simulations indicate that such synchronized perihelion windows should occur on timescales of millions of years, not decades. Yet in 2025, both objects are converging on the inner heliosphere within 28 days of each other. This has prompted a renewed debate within the planetary science community. Are we simply witnessing an extreme but natural statistical outlier? Or does the synchrony reflect deeper patterns in solar system dynamics that are not fully understood? Instrumental observations add further complexity to the picture. As 3 Atlas approached the inner solar system, spectroscopy from the Very Large Telescope, the James Webb Space Telescope and Hubble uncovered a suite of chemical signatures inconsistent with standard comet formation models. Notably, the object exhibits unusually strong diatomic carbon and cyanogen emissions, producing the green fluorescence seen in deep sky imaging. At the same time, atomic nickel was detected without the accompanying iron lines that normally appear in tandem. This separation challenges known nucleosynthetic pathways, given that nickel and iron are typically forged together in stellar environments. Swan R2 displays its own anomalies. Its rapid brightening upon emerging from conjunction indicates either a large reservoir of hypervolatile ices or an atypically porous structure that exposes fresh material to solar heating. The resulting tail extends across degrees of sky, when observed from Earth, implying significant mass loss and rapid sublimation. Yet the nucleus remains comparatively stable against fragmentation, defying predictions for such volatile, rich bodies. At ground-based observatories and space-based monitoring stations, the data describing both objects accumulate at unprecedented rates. Telemetry streams track every change in position acceleration and gas production rate. These numbers form the backbone of modern astronomical analysis, yet they cannot fully convey the unusual synchronicity unfolding above us. When considered together, the orbital geometries of both objects highlight an even more intriguing challenge. 3I, Atlas, approaches the Sun on a near ecliptic inclination of only 5 degrees, a statistically low orientation for an interstellar object. Meanwhile, Swan R2 follows a more typical long-period comet trajectory, yet intersects the inner solar system during the same seasonal window. The resulting configuration places both objects on paths that will draw them into solar glare, simultaneously effectively limiting Earth-based optical observations during the most scientifically valuable phases of their encounters. This observational blackout, driven entirely by geometry, will last for several weeks and possibly months. During that interval, solar radiation, plasma flux and tidal forces will exert maximal influence on both bodies. For 3I Atlas, this is particularly consequential as its perihelion distance of 35 AU while beyond Earth's orbit will be sufficient to substantially heat its nucleus, and potentially reveal structural or compositional traits impossible to observe at greater distances. Despite the inherent limitations, robotic missions stationed around Mars offer one advantage. On October 3rd, 3 Atlas will pass within 30 million kilometers of Mars. Orbiters equipped with high-resolution imaging systems and spectrometers will attempt to capture unprecedented details of the interstellar visitor. The results, if released without delay, could determine whether this object conforms to known cometary behavior or represents something far less familiar. Swan R2 also offers a unique observational opportunity. Its closest approach to Earth on October 21st, at only 027 AU, will enable both amateur and professional astronomers to collect detailed photometric and spectroscopic data, potentially establishing the mechanisms behind its rapid brightening and unusual tail structure. As October progresses, the scientific significance of this dual encounter becomes increasingly clear. Two objects, one interstellar, one potentially Oort-born, are approaching the Sun in the same epoch at the same seasonal moment during the same interval of heightened solar activity. The geometry is precise, the timing is unusual, the chemistry is peculiar, and the opportunity for discovery is unprecedented. Whether this convergence ultimately yields breakthroughs in our understanding of comet evolution, solar system dynamics, or interstellar chemistry remains unknown. What is certain, however, is that this moment represents a rare alignment in the long observational history of our species, one that may refine or redefine how we understand the forces shaping the space through which we travel. Modern astronomy begins not with dramatic revelations, but with quiet accumulation, photon by photon, night after night, collected by instruments designed to notice what the human eye cannot. In an era dominated by automated sky surveys and high-resolution orbital observatories, the discovery of unusual celestial objects rarely arrives as a sudden moment of astonishment. Instead, it emerges gradually, almost anonymously, from patterns hidden within terabytes of data. The dual approach of 3I, Atlas and Swan R2 has forced astronomers to reconsider how they interpret these patterns. Understanding these objects requires more than simply pointing a telescope upward. It demands an entire ecosystem of instruments, optical, infrared, ultraviolet, radio, each revealing a different piece of the cosmic narrative. To appreciate the scientific challenge of 2025's extraordinary alignment, one must first understand the mechanisms by which we detect and analyze such visitors. The Atlas survey that identified 3I Atlas operates 4 wide-field telescopes positioned across the globe. Each clear night, they capture hundreds of gigabytes of sky imagery. Sophisticated algorithms examine this data, comparing each frame to earlier baselines, searching for anything that moves contrary to the fixed star field. Most of what they find is ordinary asteroid satellites, noise, artifacts, and the steady flow of known near-Earth objects. But occasionally, something does not fit. 3I Atlas entered the scientific record as a faint pixel that moved too quickly and in the wrong direction to be gravitationally bound to the Sun. Its trajectory deviated from every catalogued object. Only after multiple nights of confirmation did it become clear that it was interstellar. Yet the Atlas survey is only one voice in a vast network. The Catalina Sky Survey in Arizona, the Pan-STARRS telescopes in Hawaii, the Linear Project in New Mexico, and the NEWISE spacecraft in Earth. Orbit all contribute to a global system of continuous monitoring. Together they act as the planet's collective observational nervous system, a distributed architecture designed to ensure no anomaly goes unnoticed. When SWAN R2 appeared in data from the Solar and Heliospheric Observatory's SWAN instrument, in early September it followed a similar pattern. The SWAN camera was never intended to discover comets. It monitors hydrogen emissions originating from interactions between solar wind and neutral atoms, but over the years its sensitivity has inadvertently turned it into one of the most reliable early warning systems for active comets. A sudden brightening in the hydrogen Lyman alpha maps often indicates a comet already outgassing strongly, long before optical telescopes observe it. This is precisely what happened with SWAN R2. Before visual astronomers could identify its structure, spectral data flagged its presence. In a sense, it was discovered not by light, but by the ghostly hydrogen envelope surrounding it, a subtle chemical fingerprint drifting thousands of kilometers from its nucleus. Each instrument that observes these visitors reveals different information. Optical telescopes show structure, coma-shaped tail-length brightness trends. Infrared instruments, like those on the James Webb Space Telescope, reveal chemical composition, thermal gradients, and sublimation rates. Radio telescopes detect ionized particles and measure dispersion caused by solar wind interactions. Together they form a multi-dimensional portrait of objects that are as transient as they are ancient. For 3i Atlas, this portrait became stranger with every data set. Webb's near-infrared spectrograph revealed a coma dominated by carbon dioxide releasing roughly 129 kilograms per second, an extraordinarily high rate at such large distances from the Sun. This alone challenged assumptions about how interstellar objects respond to solar radiation. Combined with VLT's detection of nickel without iron, a chemical imbalance rarely seen in natural environments, the object grew more perplexing. Its behaviour suggested either a formation environment radically different from our solar system, or an internal structure not yet understood. SWAN R2's observational signature also diverged from typical comet behaviour. Its tail structure evolved rapidly more quickly than classical models predict. Photometric analyses indicated sudden surges in brightness that could not be fully explained by rotational exposure of volatile-rich regions alone. In other words, something about its internal chemistry or thermal properties is unusual. While not as dramatically anomalous as 3i Atlas, its rapid evolution demands further study. Underlying all these observations is a problem of timing. As both objects approach perihelion, they enter the solar glare, the region where the sun's brightness overwhelms Earth-based telescopes. This means that the most scientifically critical phase, when heat radiation and tidal forces reveal their deepest characteristics, will occur when Earth is effectively blind. The convergence of these blackout periods has raised questions. Is this coincidence a mathematical inevitability, or does it indicate deeper patterns in how long-period objects arrive at the Sun? Mars offers the only temporary solution. As 3 Atlas passed within 30 million kilometers of the red planet on October 3rd, orbiter-mounted instruments attempted to capture data inaccessible from Earth. The high-rise camera aboard the Mars Reconnaissance Orbiter, although designed for surface imaging, provides high enough resolution to detect multi-pixel signatures of distant objects. Additional spectrometers aboard Mars Express and ExoMars Trace Gas Orbiter were configured to analyze the visitor's emissions. These datasets, if released publicly, may ultimately provide the clearest imagery of an interstellar object ever obtained. But as of late October, no consolidated results have been published. Whether this delay reflects technical complexities, data quality issues, or administrative bottlenecks remains unclear. In earlier decades, such delays would pass unnoticed. But in the age of instantaneous public data access, silence naturally generates speculation. The broader scientific context, however, is clear. These dual arrivals underscore the necessity of understanding how the solar system interacts with external objects. Interstellar visitors carry chemical memory from environments far beyond our own. Their behavior under solar radiation provides invaluable information about early stellar systems, volatile preservation, and physical responses to heat and magnetic fields. SWAN R2, despite its local origin, offers complementary insights. Its spectral and structural irregularities help refine models of comet evolution, sublimation physics, and thermal stress responses. Together, the two objects form an unexpected natural experiment, an alignment of unrelated processes that collectively illuminate the larger mechanisms shaping celestial dynamics. Ultimately, the convergence of 3I Atlas and Swan R2 in October 2025 reveals not only the complexity of the objects themselves, but the sophistication and limitations of our observational systems. It demonstrates that even with the most advanced instruments in human history, the universe retains its capacity to surprise and to conceal precisely when answers seem closest. In astronomy, chemistry becomes a language and light becomes the page on which it is written. Each atom, nickel, iron, carbon, cyanogen, speaks in signatures etched across the electromagnetic spectrum. Through spectroscopy, these signatures reveal origins, histories, and the physical conditions shaping celestial bodies. For 3I Atlas, this language has been both illuminating and perplexing. When the Very Large Telescope first aimed its spectrographs at the interstellar visitor, astronomers expected a familiar composition. Interstellar comets, though rare, are assumed to mirror the chemical fingerprints seen in objects from our own solar system shaped by the same universal nuclear processes. The surprising truth emerged quickly. 3 Atlas was fluent in an unexpected dialect. Its spectrum displayed strong nickel emissions glowing prominently in the green portion of the visible spectrum, yet iron, which should accompany nickel in predictable cosmic proportions, was effectively absent. This imbalance contradicts the elemental ratios forged in supernovae, the processes that scatter heavy metals throughout the galaxy. In nearly every natural sample, from meteorites to comets, like 2I Borisov nickel and iron travel together. Their atomic ratio serves as a record of the star that birthed them, but 3 Atlas broke this rule. A comet glowing with nickel but nearly silent in iron suggests either selective depletion or preferential release, neither of which fits comfortably within existing models. Some researchers proposed chemical pathways that might liberate nickel more readily than iron under solar heating nickel-carbonyl complexes, exotic organometallic reactions, or long-term space weathering altering surface chemistry on microscopic scales. Others urged caution, noting that interstellar objects may form under conditions radically unlike those of our solar system. In environments colder, darker, or richer, in certain volatiles, the chemical evolution of icy bodies could take unusual turns. The James Webb Space Telescope deepened this mystery. Its infrared observations found carbon dioxide dominating the coma, with surprisingly little contribution from water vapor at large distances. This pattern is consistent with heavily layered ices where the most volatile materials sublimate first, but the relative abundance still diverges from what researchers expect, even for distant object activation. The carbon-rich nature of the visitor raises questions about its birthplace, perhaps a region of a distant stellar nursery where temperatures remained low enough for CO2 ices to accumulate in unusual concentrations. Cyanogen, another contributor to the green emission, complicates the picture further. CN radicals, while common in cometary environments, appear in strengths difficult to reconcile with typical formation scenarios. The brightness curve of 3I Atlas shows subtle but persistent deviations, small surges, irregular declines that hint at compositional patches or subsurface activation events. These signals resemble natural outgassing patterns, yet their cadence remains oddly consistent. As observational campaigns expanded data from amateur astronomers, high-resolution photographs taken from backyards and mountain ridges added to the global mosaic. These enthusiasts have become essential collaborators in modern comet science. Their nightly monitoring supplies temporal continuity that large observatories cannot match. Their images reveal coma asymmetries and faint tail structures, confirming that whatever chemical story 3I Atlas tells, it evolves dynamically. Swan R2, while less chemically anomalous, presents its own deviations. Its rapid brightening, irregular tail development, and unexpectedly fast activation upon emerging from the sun's glare suggest a body with volatile properties not entirely aligned with classical Oort cloud models. It is as if both visitors, one interstellar, one homegrown, carry chemical accents foreign to the typical dialects of their respective origins. Yet despite these peculiarities, the scientific community remains cautious. NASA and ESA have repeatedly emphasized that unusual does not equate to unnatural. Interstellar visitors are statistically sparse. Studying only 3 in modern history means we lack a baseline for what should be typical. What appears anomalous may in fact be perfectly normal for bodies formed around distant stars. This perspective is supported by the precedent of Borisov, whose own chemistry, particularly its elevated carbon monoxide levels, challenge assumptions about universality in comet formation. When viewed through this historical lens, 3I Atlas becomes less an outlier and more a reminder of how little is known about the diversity of planetary systems scattered across the galaxy. These scientific nuances often dissolve when filtered through public discourse. The nickel without iron signature, for example, circulated widely on social media, has suggested evidence of metallic alloys, engineered structures or artificial processing. The idea that 3I Atlas might represent a technological artifact, an ancient probe, or a disguised machine captured public imagination. Yet no spectroscopic data supports this interpretation. Natural pathways, though complex, remain sufficient. Still, the questions remain. Science progresses because anomalies demand explanation. Even if all evidence ultimately supports natural origins, the process of investigation deepens our understanding of chemistry, physics, and the diversity of environments that shape celestial bodies. As October advances, the challenge grows. Both objects slowly descend into the sun's overwhelming light, slipping into an observational silence where instruments cannot follow. The chemical language of 3I Atlas. The unusual nickel lines, the layered volatiles, the ambiguous green glow may remain unreadable for weeks or months. Only when the visitor emerges from solar conjunction will astronomers resume deciphering its spectral story. And when they do, they will listen again not only for answers but for the next question hidden within the light. In the mechanics of the solar system, coincidence is often stranger than intention. A single comet sweeping through the inner system hardly draws attention. Long-period objects from the Oort cloud drift inward with seasonal regularity. Even an interstellar visitor, though remarkable, is statistically inevitable on cosmic timescales. But the convergence of 2 unrelated bodies, one born in the outer reaches of our own system, the other arriving from interstellar space approaching the Sun within mere weeks of one another, creates a puzzle that invites deeper reflection. October 2025 presents such a moment, 2 paths independent in origin threading themselves through the same narrow corridor of time. 3I Atlas arrived first. It emerged in early July from the direction of Serpent's Tail, with a trajectory that immediately set it apart. Its orbit was sharply retrograde inclined, nearly 175 degrees relative to the planetary plane. It moved against the flow, an unmistakable signature of an object that was not born in the solar system. Its hyperbolic path confirmed this, marking it as an interstellar wanderer, one that would visit briefly before returning forever to the void between stars. By the time surveys caught its faint green smudge, it was already well inside Jupiter's orbit, having travelled months unseen, through regions too close to the Sun's glare for effective detection. Swan R2, in contrast, followed a far more familiar pattern. This comet originated from our own Oort cloud, and spent most of its life frozen in darkness before perturbations nudged it inward. Its approach was hidden by the Holacek effect, a geometric bias that conceals brightening comets until their orbits carry them safely away from the Sun's blinding radiance. When Swan R2 finally emerged in September, it did so dramatically. Its brightness rose quickly, its tail unfurled across degrees of sky, and binocular observers around the world reported a spectacle rarely seen in modern skies. The physical and orbital contrast between the 2 objects could not be sharper. 3I Atlas is compact, its nucleus likely only a few kilometers across. Its activity is subtle, its green tint a whisper from the chemistry of carbon molecules fluorescing under solar light. Swan R2 by comparison is expansive, a vast luminous veil shaped by sunlight and solar wind stretching millions of kilometers into the night sky. One is a quiet visitor, the other a performer. Yet despite these differences, their trajectories bring them into a surprisingly tight temporal sequence. Swan R2 reached perihelion on September 12th. 3 Atlas will pass near Mars on October 3rd, then sweep into its closest solar encounter around October 29th or 30. Swan R2, meanwhile, will pass closest to Earth on October 21. In a span of about 6 weeks, both objects cross critical thresholds, perihelion planetary flyby closest approach. It is a celestial choreography that feels almost deliberate. But in the domain of celestial probability, unlikely does not mean impossible, nor does it imply meaning. Interstellar objects can approach from any direction, often detected late because of their unpredictable geometry. Long-period comets brighten only when close enough to activate. The convergence of detectability, not origin, may be what binds them. One emerges from glare, the other becomes luminous enough for our instruments, and both by chance enter observational reach within the same season. Still, the timing invites curiosity. Astronomy has always balanced empirical rigor with a sense of wonder. Even seasoned researchers admit that the narrative symmetry is striking a needle of interstellar light and a sprawling comet from our own cosmic backyard, arriving together at the inner solar stage. But physics remains steadfast. Orbital calculations reveal no shared influence, no gravitational coupling, no signs of interaction. They are two trajectories intersecting in time, not in space. Observation, however, is ephemeral. As October deepens, both objects will approach the sun's glare and slip behind it. Solar elongation shrinks. Ground-based telescopes lose sensitivity. The most dynamic phases of cometary activity, the intense heating, rapid outgassing potential fragmentation, will unfold in a region where our instruments cannot reach. This blackout and unavoidable consequence of geometry adds an element of suspense. If anything unusual were to occur, we would be unable to witness it directly. Mars, however, will receive a privileged view. On October 3rd, 3:16, Atlas will pass within 30 million kilometers of the red planet. This is distant in human terms, but tantalizingly close for interplanetary spacecraft. Orbiters such as Mars Reconnaissance, Orbiter ExoMars and Mars Express may attempt opportunistic observations. Their instruments, though not designed to track deep space visitors, could capture valuable data, spectra dust profiles, tail structures revealing aspects invisible from Earth. This interplanetary triangulation, Earth fading into observational blindness while Mars rises into position, creates a scientific moment shaped by both limitation and opportunity. When the visitor re-emerges months later, its coma-tail brightness and spectral lines will reveal what occurred in the hidden weeks behind the Sun. In considering the convergence of 3I Atlas and Swan R2, the mind naturally wanders toward broader reflections. Gravity is indifferent to narrative. Radiation does not orchestrate coincidence. Yet human perception seeks meaning in alignment. We connect patterns because the night sky has always been a mirror for human thought. And so the arrival of two independent wanderers may feel like a duet, a cosmic metaphor, even if science insists on independence. In truth, the universe is full of such moments, brief intersections, that highlight the quiet beauty of the celestial clockwork. Their convergence is neither omen nor design, but a reminder that chance itself is part of the cosmic structure. And in that structure, even improbable alignments can unfold with elegance. In every age of astronomy, the sky has offered questions long before it offered answers. When two unusual objects arrive in the inner solar system at nearly the same time, one interstellar, one from our own deep cloud, the human mind begins to search for patterns, meaning stories that might explain what pure physics leaves unsaid. This instinct is not a flaw. It is one of the oldest impulses in scientific thought. Where data ends, imagination begins mapping possibilities, like drawing constellations across an unfamiliar sky. The convergence of 3R Atlas and Swan R2 in October 2025 has inspired just such a spectrum of interpretations. Some are grounded in cautious analysis, others in speculative frameworks, shaped by decades of thinking about extraterrestrial intelligence and cosmic engineering. Each theory attempts to bring coherence to coincidence, to understand whether this overlap in time is merely statistical happenstance or something more intentional. And in examining them, we learn as much about human psychology as we do about the visitors themselves. One of the more provocative ideas casts 3I Atlas as a reconnaissance craft, a small maneuverable probe travelling ahead of a larger system. In this view, Atlas is the scout and Swan R2 the fortress, a mobile platform capable of power generation, data storage or resource processing. Their timing becomes choreography, The Scout arrives first to assess stellar conditions, the larger structure following to complete an operation that requires coordination under intense solar energy. This perspective arises because 3i Atlas exhibits precision, its trajectory, sharp its approach, swift its chemistry, unexpected. Swan R2, by contrast, is vast, a sprawling coma, a spectacular tail, a presence more consistent with a body that might conceal complex systems beneath a screen of natural outgassing. The pairing feels almost deliberate, a scalpel and a city. Another speculative model imagines both objects as part of an ancient automated infrastructure, a kind of cosmic maintenance cycle. In this framework, interstellar space is populated not only by stars and planets, but by technology drifting across epochs, performing scheduled tasks set in motion millions of years ago. 3i Atlas could be a diagnostic unit designed to survey solar systems for changes in stellar output or planetary conditions. Swan R2 could function as a repair vessel carrying materials or energy systems that activate only during perihelion when sunlight provides peak power. If such a system existed, it might operate without any living designers remaining. Its creators could be long gone. What remains might be autonomous machinery executing scripts beyond the lifespan of the civilizations that built them. Other interpretations lean toward communication rather than engineering. If humanity has indeed been broadcasting radio signals into the cosmos for nearly a century, our electromagnetic bubble now extends roughly 100 light years. To any listening system, this bubble would mark the presence of an emerging technological species. The arrival of 3i Atlas and Swan R2 could then represent a reply not deliberate in the sense of conscious intent, but as part of an automated listening network that responds to new sources of artificial emission. The timing would fit decades for detection, decades for transit arrival, aligning with the point at which humanity's signals become unmistakable. Still others place these visitors within mythic frameworks. Human cultures across time have told stories of twin omens paired comets, or dual celestial messengers appearing before significant historical transitions. In this reading, Atlas and Swan R2 become modern expressions of ancient archetypes, harbingers, not of doom, but of change. Their dual arrival symbolizes thresholds between ignorance and understanding, between solitude and cosmic awareness. All these interpretations, however imaginative, must stand against the weight of observation. And observation so far supports natural explanations. NASA and ESA have remained consistent, no detected accelerations inconsistent with gravity, no radio emissions suggestive of artificial systems, no spectroscopy revealing manufactured materials. The unusual chemistry of 3i Atlas, its nickel without iron, its CO2-rich volatiles, can be reconciled with natural pathways formed under extreme conditions around distant stars. Swan R2's rapid brightening, though striking, aligns with known behaviour in long-period comets emerging from solar conjunction. Yet the psychological influence of unusual phenomena is undeniable. When objects appear at the edge of human knowledge, they invite stories. And the more ambiguous the data, the more room imagination has to expand. Social media amplifies small anomalies into grand hypotheses. Preliminary chemical signatures become evidence of metal alloys. Light curves become flight patterns. A coincidence becomes a signal. It is here in the space between evidence and interpretation that astronomy reveals its philosophical dimension. The human mind seeks purpose, not because the universe is purposeful, but because humans are. Our ancestors found meaning in constellations. We find meaning in orbital intersections. The impulse is the same, to bring coherence to the infinite. Still, even the most speculative theories must confront the reality of observational gaps. The most crucial phases of both objects' journeys, their perihelion passages, will take place behind the Sun, unreachable by direct imaging from Earth. This period of solar conjunction creates a silence that the human mind instinctively fills. In that silence, any scenario seems plausible, whether rooted in astrophysics or science fiction. But silence itself is data. The absence of artificial signatures may be mundane, or it may simply reflect limits in our detection methods. After all, technology thousands or millions of years ahead of our own could resemble natural processes so closely that distinguishing between them becomes nearly impossible. Advanced engineering might not violate physical laws but instead manipulate them with elegance beyond our recognition. And so the October convergence becomes not just an astronomical event, but a philosophical mirror. Whether the visitors are natural, artificial, or something in between, the real revelation may concern our response to the unknown. Do we default to skepticism or imagination? Do we see randomness or narrative? Do we interpret silence as emptiness or as potential? In the end, the scientific method remains our anchor. Data must precede theory, and interpretations must yield to measurements. Yet imagination has its place too. It propels inquiry, shapes new questions, and expands the horizon of what we are willing to consider. The sky in October 2025 does not ask us to choose between wonder and rigour. It asks us to hold both, as humanity always has when faced with the vastness of things not yet understood. The story of 3A Atlas begins with something almost laughably small, a single pixel changing brightness on a CCD detector in the Chilean desert. Not a streak, not a flare, just one faint point of light that shouldn't have been there. Yet this is how many cosmic stories begin in the modern age. The universe does not announce its arrivals with thunder. It slips quietly into the margins of data, waiting for someone patient enough to notice the difference between noise and a new world entering our field of view. On July 1st, 2025, one of the Atlas survey telescopes recorded that faint anomaly. Atlas, designed primarily to detect potentially hazardous asteroids, scans the sky with mechanical loyalty, comparing every frame against catalogues of thousands of known objects. Its purpose is simple: find what moves, what brightens, what deviates from expectation. And on that night, something did. Within hours, automated software flagged the point of light as unusual. Its motion across sequential images was too fast for a distant asteroid, yet too slow for a near-Earth object. The trajectory, once calculated, revealed something astonishing. This visitor was not bound to the Sun at all. Its orbit was hyperbolic, a signature marking it as only the third confirmed interstellar object in recorded human history. Already the narrative had shifted. A faint pixel became a messenger from another star system. Orbital reconstruction traced its path backwards, suggesting that 3I Atla had entered our solar system months earlier, perhaps even in late 2024, slipping invisibly through regions too close to the Sun for our telescopes to monitor. That invisibility is not unusual. Interstellar objects can approach from arbitrary angles, often emerging from solar glare just before discovery. By the time Atlas detected it, the visitor was already inside Jupiter's orbit, long past the point where early detection might have revealed more about its origin. Its inclination, approximately 175 degrees, offered another clue. The object was travelling retrograde, moving opposite the direction of planetary motion, as if swimming upstream through the solar system's gravitational current. This behaviour is nearly impossible for native objects which form from the same primordial disk, and thus share more or less the same direction of travel. Retrograde interstellar trajectories are not surprising, but they do highlight the foreignness of the visitor. Everything about 3 Atlas hinted at a deep past far beyond our Sun. As astronomers refined its orbit, they realised that its closest solar approach, its perihelion, would occur in late October 2025 at roughly 1.35 astronomical units. This is inside the orbit of Mars, unusually close for an interstellar object. Most visitors from other stars pass at far greater distances. The geometry of this encounter, though dangerous for observational visibility, promised a rare chance to study the chemistry, dynamics and morphology of a body shaped by the environment of another star. The path of 3I Atlas also brings it into a near rendezvous with Mars on October 3rd, sweeping past the red planet at a distance of about 30 million kilometres. Though far from dramatic in human terms, this distance places the object within observational reach of orbiting spacecraft, an opportunity that planetary scientists have seized eagerly. Instruments aboard NASA's Mars Reconnaissance Orbiter, ESA's ExoMars Orbiter, and even the aging Mars Express may attempt to capture data during the brief window when the geometry aligns. But observations from Mars come with limitations. These spacecraft were built to study a planet, not a visitor from interstellar space. Their pointing mechanisms, spectrographs and imaging systems can only do so much when targeting an object millions of kilometers away. Yet even partial data, shifts in brightness, hints of tail structure spectral absorption features could reveal aspects invisible from Earth. From Earth's perspective, the observational timeline is tight. Ground-based telescopes track the visitor intensively through July-August and early September. Hubble captured high-resolution imagery constraining the size of the nucleus to just a few kilometers. JWST observed the infrared signature of its outgassing detecting carbon dioxide dominance at distances where water remains frozen. The Very Large Telescope dissected its light, uncovering the strange nickel emissions that have since sparked so much debate. Together, these instruments painted a picture of an object chemically unusual, dynamically foreign, and scientifically irresistible. But now, as the sun grows closer to the line of sight, the window begins to close. By mid-October, solar glare will overwhelm Earth-based telescopes. A period of forced silence will begin. The object will slip behind the sun's radiance, unobservable for weeks, perhaps months. Its evolution during perihelion, the most volatile phase of its journey, will occur largely out of sight. This blackout is not unusual. It is one of the recurring frustrations of cometary science. The sun, for all its warmth and light, is also a veil. It hides what we most want to see. When 3I Atlas emerges again in December, its shape, brightness and chemistry will tell the story of what happened in that hidden interval. Some objects fragment under intense heating, others brighten dramatically, some darken and fade. A few survive unchanged. Interstellar objects, having spent millions of years exposed to cosmic rays between stars, might behave differently from comets born within the protective cocoon of the solar system. Astronomers do not know which outcome to expect. What they do know is this 3I Atlas represents a messenger from a region of space we have never touched, a chemical archive, from a star system whose name we do not know. Its orbit tells of a long journey, its composition tells of temperatures and pressures alien to us, and its presence entering our solar system just as Swan R2 brightens into view tells of a universe in which coincidences still have the power to humble. In the end, the true significance of 3I Atlas may not lie in any anomaly or mystery, but in the reminder it brings. We live inside a cosmic crossroads. The space between stars is not empty. It is a slow river of objects, each carrying a story written in dust, ice metal and motion. And every so often, one of those stories drifts close enough for us to read a few pages before it disappears again into the dark. The universe writes its messages in light, and 3I Atlas has been speaking in a shade of green that refuses to be ignored. Since its discovery, observers around the world have noted the comet's subtle but distinct emerald glow, a phenomenon not unprecedented yet striking enough to spark renewed discussion about the chemistry of objects that come to us from other stars. Colour in astronomy is never merely aesthetic. It is a signature, a clue, a spectral fingerprint that encodes the physics of excitation and the histories of ices buried for millions of years. In the case of 3I Atlas, the green hue likely arises from diatomic carbon C2 fluorescing under solar ultraviolet radiation. This phenomenon is well known in comets, a byproduct of organic molecules breaking apart as sunlight warms the coma. But cometary colour is more than pigment. It reflects the conditions of freeze out in stellar nurseries, the accumulation of carbon-bearing volatiles in cold molecular clouds, and the layered structure of ice that forms as an object grows in a distant protoplanetary disk. The brightness and persistence of Atlas's green emission, however, have kept scientists watching closely. Subtle deviations in spectral ratios hint at processes that may not perfectly align with solar system norms. Then came the discovery that moved the conversation firmly into scientific intrigue: the presence of nickel vapour without its natural companion iron. In nearly all known environments, from planetary cores to meteorites to ordinary comets, nickel and iron appear together. Both are forged in the intense nuclear furnaces of massive stars. Both condense out of the same cooling gas clouds. Their ratio across our solar system is remarkably stable, yet in the spectrographic data from the Very Large Telescope, strong nickel lines appear cleanly and confidently, while iron remains conspicuously silent. Interpreting this absence is not straightforward. Some researchers suggest that nickel-bearing compounds might sublimate more readily than iron-rich ones under the thermal conditions Atlas currently experiences. Others propose surface fractionation processes, micrometeorite impacts, or millennia of exposure to interstellar radiation that could strip away volatile iron-bearing layers or restructure grain surfaces. Still others favour chemical pathways involving nickel carbonyls capable of releasing nickel atoms efficiently when heated. None of these explanations are impossible. All require deeper investigation. Meanwhile, the James Webb Space Telescope continued painting a portrait of the visitor that feels both familiar and foreign. Its infrared instruments detected abundant carbon dioxide sublimation at heliocentric distances where solar system comets typically show water as the dominant volatile. This CO2-rich activation suggests that Atlas formed in unusually cold regions, likely farther from its original star than Earth is from the Sun, and possibly under conditions where carbon-bearing ices accumulated in quantities rare in our neighbourhood. Water, the hallmark of solar system comets, has so far been a minor component in Atlas's coma. This does not imply its absence. Rather, it suggests deeply buried layers that will not awaken until the comet approaches much closer to the Sun. What we are seeing now is the early activation of outer layers volatiles that require only modest heating to begin sublimating. These first vapours carry stories frozen into place long before our solar system existed. The complexity deepens with the presence of cyanogen. CN radicals, while common in comet spectra, appear in strengths that raise questions about the organic inventory of the Atlas nucleus. Cyanogen's glow, also green, adds to the object's distinctive coloration. Its abundance relative to C2, CO2 and water becomes an important diagnostic tool for understanding the chemical environment of the comet's birthplace. Ratios between these molecules hold clues to pressure density and temperature conditions in regions of interstellar space that JST cannot directly probe. But for all the advanced observatories contributing to the story, one of the richest sources of data remains the global community of amateur astronomers. High-quality backyard images taken night after night provide temporal continuity that large telescopes cannot match. Subtle changes in the coma's colour and brightness, the appearance of new jets, the shifting architecture of the tail, all become visible through the patient persistence of thousands of observers watching from rooftops, deserts and mountain slopes around the world. Their photographs reveal structure, where professional instruments reveal composition. Together they form a tapestry of observation that spans continents and cultures. With Swan R2 the chemistry is different but equally instructive. Its rapid brightening upon emerging from conjunction suggests a volatile inventory unusually rich in dust and gas. The speed of its activation resembles comets that have spent eons in deep freeze before encountering sunlight abruptly. Its tail development stretching across degrees of sky contains embedded structures that hint at disconnection events, moments when magnetic field interactions tear segments of the ion tail away before solar wind pressure rebuilds it. These events mirror processes seen in previous great comets, but in Swan R2 they appear earlier and more frequently than models predict. Yet despite many unusual details, agencies remain cautious. NASA emphasises that none of the chemical signatures from either object require technological explanations. The anomalies fall within the outer edges of what is theoretically possible for natural bodies. ESA echoes the sentiment interstellar objects with their wildly varied formation environments may easily display chemistries our solar system simply isn't used to. The sample size of such visitors is too small to define a standard against which all newcomers must conform. Still, anomalies have a gravity of their own. They attract attention, speculation and wonder. They push the boundaries of what we think we understand and remind us that chemical diversity across the galaxy is vast. What feels unusual to us may be ordinary elsewhere. As October approaches and both objects descend into the sun's glare, their chemistry will evolve rapidly. Solar heating will awaken deeper layers of ice. New volatiles will emerge. Jets may activate or shut down. Fragmentation remains a possibility during extreme thermal stress. And through all of this, our ability to observe narrows daily. Soon spectroscopy will fall silent. Photometry will be overwhelmed. The most interesting phase of their chemical story may unfold entirely out of sight. When the visitors reappear in November or December, their colours may shift, their volatiles may change, their light curves may tell of stresses and transformations that occurred in the furnace of perihelion. In that sense, the chemistry of 3I Atlas and Swan R2 is not only a property, it is narrative. A story of ice and radiation, of molecules older than the sun, of reactions that began long before humans learned to watch the sky. October 3rd, 2025 marks a moment that seems almost scripted. An interstellar traveller, after millions of years wandering the void between stars, will sweep past Mars at a distance of approximately 30 million kilometres. For the human imagination, this number feels both intimate and impossibly vast. For planetary science, it represents an extraordinary opportunity, one that cannot be replicated, rehearsed or delayed. In the quiet choreography of the solar system, Mars has happened to drift into the right place at the right time. And because of this, machines orbiting the red planet may become the only active witnesses to a visitor from another sun. In absolute terms, the distance is large, 5 times the span between Earth and the Moon. No spacecraft will see the object as anything more than a slender smear of reflected sunlight. But at interplanetary scales, closeness is not measured in kilometres, but in geometry. The encounter gives Mars-based spacecraft a rare vantage point, an angle unachievable from Earth, where solar glare will soon swallow Atlas completely. Even imperfect observations from Mars may reveal details inaccessible to telescopes constrained by Earth's orbit and atmosphere. The European Space Agency has already begun planning for this moment. Instruments aboard the Trace Gas Orbiter, designed originally to analyse methane and atmospheric chemistry, can be repurposed to study the dust and gases escaping from Atlas's coma. Mars Express, one of the oldest continuously active spacecraft in the solar system, carries spectrometers capable of capturing the faint signatures of molecules sublimating from the visitor's nucleus. NASA's Mars Reconnaissance Orbiter, with its high-resolution imager HiRISE, offers the tantalizing possibility of capturing coma structure from a vantage point above the Martian sky, though the distances involved will test the limits of its sensitivity. These spacecraft were never intended to study interstellar objects, yet the history of space exploration is filled with observations made on borrowed time. Instrument teams must carefully program new pointing maneuvers, balance power constraints, and navigate communication delays that stretch to more than a dozen minutes each way. In the silence between command and response, the spacecraft must execute instructions autonomously, tracking a target that moves faster than any asteroid normally observed from Mars. Despite the allure of the encounter, expectations must remain grounded. The visitor will still appear faint even from Mars. Surface details of the nucleus will remain beyond reach, as will any fine structure smaller than hundreds of kilometres. The data will consist of changes in brightness, subtle enhancements in coma, colour, possibly faint streaks revealing tail direction relative to the solar wind. Yet within these modest datasets lie clues that astronomers hunger for: variations in dust grain size, the presence or absence of specific volatiles, the symmetry or asymmetry of outgassing jets. For interstellar objects, outgassing behaviour can be particularly revealing. Their ice is formed under conditions unlike anything present in our solar system. Their sublimation thresholds, activation sequences and molecular abundances offer glimpses of other suns, other disks, other beginnings. From Earth spectroscopy has already hinted at exotic chemistry within Atlas. Mars may allow us to confirm or refute those early interpretations as the visitor enters a regime of heating far more intense than it has yet experienced. The geometry of the flyby also offers another scientific gift: the ability to study ion-tail interactions from a unique angle. When a comet interacts with the solar wind, the resulting ion tail aligns roughly along the direction of that flow. Viewing it from different vantage points such as Earth and Mars allows researchers to reconstruct three-dimensional structures rather than relying on a single plane of observation. Changes in tail curvature, fragmentation of ion strands and discontinuities, caused by magnetic reconnection events, all provide evidence of how the object responds to the heliospheric environment. Yet for all this potential, the encounter carries a quiet melancholy. The Mars flyby occurs just as Earth's telescopes are beginning to lose visibility. dust and gas that would otherwise be scrutinized in exquisite detail will drift unnoticed through heliocentric space. The most dramatic stages of solar heating, when the object begins to shed material rapidly, when jets open or collapse, when stress fractures begin to propagate, may occur entirely behind the Sun. Mars will see only a prelude. There is also the challenge of timing. Mars orbiters can capture only brief windows of observation. The spacecraft circle the planet every few hours, and their instruments face outward for only a fraction of each orbit. Even under ideal circumstances, the flyby offers perhaps minutes of meaningful data scattered across a handful of observation cycles. If dust storms sweep across the Martian surface, as they often do in October, they may interfere with spacecraft pointing obscure star trackers or reduce the stability of fine instrument control. Still, scientists persevere, because even a few minutes of imperfect data hold more scientific value than hours of speculation. If Atlas brightens unexpectedly, Mars may detect it. If the visitor shows strange asymmetries, Mars may glimpse their signature. If outgassing becomes more violent than models predict, Mars may capture the early stages of the eruption before the object disappears behind the Sun entirely. The encounter also underscores the growing importance of distributed observation in planetary science. No longer is the Earth the sole anchor of astronomical study. As humans continue placing instruments around other planets, every alignment, every flyby, every cosmic coincidence becomes an opportunity to expand the observational baseline. A visitor like 3Y Atlas becomes not just an object of study, but a test of our multiplanetary capability, our ability to coordinate instruments across worlds. And so the Mars flyby becomes more than a footnote in the story of two cosmic visitors. It becomes a moment of quiet collaboration between planets, one illuminated, one observing, both linked through the thin lines of radio transmission and scientific curiosity. An interstellar wanderer drifting past a silent desert world, being watched by machines whose creation was driven by the same species, now staring upward from Earth, wondering what this visitor truly represents. When the data eventually returns days or weeks after the encounter, it will arrive wrapped in uncertainty and promise. Scientists on Earth will sift through it pixel by pixel, searching for signs of structure, chemistry, and evolution. And in the faint patterns encoded in those images, we may find not answers, but better questions. While 3I Atlas captured attention with the mystery of its interstellar origins, another object larger, brighter, and far more theatrical was quietly preparing to dominate the night sky. Swan R2, discovered almost by accident in solar wind, imaging data emerged from the Sun's glare in September 2025 with a brilliance that felt almost sudden. It was not a subtle visitor, not a faint whisper of a comet barely visible through telescopes. Swan R2 arrived like a curtain rising on a cosmic stage, revealing a luminous structure already in full bloom. Its discovery story speaks to the evolving partnership between professional astronomy and the global community of dedicated amateurs. Vladimir Psugli, an astronomer working not from an observatory dome but from a computer terminal, first noticed an unexpected brightening in SOHO's Swan instrument imagery. Swan, built to map the distribution of hydrogen created when solar ultraviolet radiation breaks apart. Water molecules is not designed for comet hunting, yet its sensitivity to hydrogen makes it uniquely capable of detecting comets too close to the Sun for traditional telescopes. In this case, that sensitivity allowed Swan R2 to be spotted while still hidden deep in solar glare. When the comet finally emerged into the twilight skies near the constellation Virgo, its brightening was unmistakable. The coma expanded rapidly. The tail lengthened into a luminous banner stretching as much as 2 degrees across the sky, 4 times the apparent diameter of the full moon. Amateur observers with binoculars reported seeing structure within the tail knot's disconnection events and subtle curvature shaped by the shifting direction of the solar wind. The comet was evolving daily, almost hourly, its appearance shaped by dynamic interactions between solar radiation magnetic fields and the volatile ices awakening within its nucleus. Swan R2 is a long-period comet likely originating from the Oort cloud, the vast spherical reservoir of icy bodies surrounding the solar system. These comets spend the majority of their existence in near-absolute darkness, preserving chemical inventories from the era of solar formation. When gravitational nudges send them inward, they begin a slow, unpredictable conversation with sunlight. Each volatile layer, carbon monoxide, carbon dioxide, ammonia, water, activates at a different temperature. As they heat unevenly, pressure builds within the nucleus, creating jets and plumes that sculpt the coma and tail. For Swan R2, the activation was unusually rapid. By mid-September, it had already surpassed magnitude 6, making it visible to the naked eye from dark locations. Predictions suggested that by late October, during its closest approach to Earth, at only 0.27 astronomical units, it could brighten into the range of magnitude 4 or 5, a rare event in modern cometary observing. Yet brightness tells only part of the story. Comets are laboratories of chemical history, and Swan R2's behaviour reflects a complex interior, shaped by billions of years of cryogenic storage. Its tail revealed two distinct components, a dust tail curved and heavy, pulled by the pressure of sunlight, and an ion tail thin and straight, driven by interactions with the solar wind. Disconnection events, moments when magnetic realignment snapped the ion tail and caused it to reform, offered valuable clues to both cometary chemistry and solar activity during this period. Professional observatories began to coordinate observations to complement amateur imaging. Though 3i Atlas remained the more scientifically exotic object, Swan R2 offered opportunities to study pristine Oort cloud material under conditions of intense solar heating. Spectrographs searched for signatures of carbon chains, water isotopes, and organic precursors. Photometric studies tracked the brightness curve for evidence of outburst cycles or thermal stresses. The comet responded with a performance both familiar and unpredictable, embodying the dual nature of long-period comets, partly understood, partly wild. The orbital mechanics of Swan R2 added another layer of intrigue. Its perihelion on September 12th brought it to within half an astronomical unit of the Sun. At that distance, temperatures rise dramatically. Ices trapped deep within the nucleus for billions of years are suddenly liberated. The comet becomes a machine for turning solid into gas, and this transformation can lead to fragmentation, temporary jets, or even structural instability. Observers worldwide monitored the comet for signs of such behaviour, aware that many bright comets fade prematurely when their nuclei fracture under thermal stress. So far, Swan R2 has held together. But comets are notoriously unpredictable. Their evolution near perihelion follows physics that is simple at its core. Heat triggers sublimation, yet complex in execution, shaped by microstructure spin states and irregular internal layering. This tension between predictability and chaos is part of what draws astronomers to study them. They are ancient archives, yes, but they are also living bodies of ice and dust, responding dynamically to their changing environment. The timing of Swan R2's arrival parallels that of 3i Atlas, in a way that has inspired more than scientific interest. Two bright visitors at once, one foreign, one native, one a needle of green light, the other a sweeping banner of dust. Their near-simultaneous passage through the inner solar system has created an unprecedented opportunity for comparative study to very different objects undergoing similar physical transformations under similar solar forcing. Yet for most of the public, the science may matter less than the simple beauty of the sight. Comets have inspired humans for millennia, long before spectroscopy turned their colours into chemistry, and orbital mechanics replaced omens with equations. Swan R2, with its wide drifting tail and soft glow, reconnects modern observers with that older tradition, the quiet awe of looking up and seeing something transient yet timeless, ancient yet newly arrived. As October progresses, Swan R2 will continue its outward journey. Its brightness may remain strong for weeks or fade rapidly. Its tail may lengthen or fragment. Its nucleus may survive or break apart unseen behind the sun. Whatever happens, it will leave behind data images, spectra brightness curves that scientists will analyse long after the comet has faded from memory. And perhaps somewhere in that data lies a clue, not only to the comet itself, but to the broader question posed by this remarkable autumn: why in a solar system governed by probability and chaos did two such different visitors arrive together? When unusual visitors enter the inner solar system, one from interstellar space, the other awakening in a brilliance rarely seen, speculation inevitably expands to fill the silence between data points. most explanations remain grounded in natural processes, sublimation curves, orbital mechanics, solar heating. Yet for centuries humanity has imagined machines disguised as comets, probes drifting between suns, fragments of ancient civilizations that seeded the galaxy and left behind artifacts that resemble natural bodies, because nature itself is the most efficient engineer. The present moment with 3I Atlas and Swan R2 converging in time invites a careful, sober exploration of what such possibilities might look like, and why science, while open to imagination, continues to lean toward natural explanations. If an advanced civilization sent machinery across interstellar distances, the most energy-efficient strategy would be to hide within objects that already traverse those paths. Natural comets and icy planetesimals offer shielding mass and camouflage. A machine embedded within a comet would benefit from thermal inertia protection against micrometeoroids and natural forms of propulsion driven by sublimation. In this speculative framework, the distinction between natural and artificial becomes blurred. An engineered system might appear indistinguishable from an ordinary comet if it uses physical processes already present in the object. One hypothetical signature of artificial propulsion would be sustained non-gravitational acceleration, a deviation from orbital predictions that cannot be explained by outgassing alone. With 1IU Muammer, this subtle acceleration sparked debates about whether outgassing could account for its behaviour. With 3I Atlas, no such anomaly has been detected. Its motion aligns with natural models. The object follows an elegant hyperbolic path dictated by gravity, showing no sustained acceleration inconsistent with sublimation. The data remains stubbornly ordinary even if the chemistry feels unusual. Another signature would be coherent electromagnetic emissions, the kind produced by transmitters or field generators. Radio telescopes have listened quietly, methodically, without expectation. They have heard nothing unusual from either object. Not a pulse, not a periodic signal, not even a narrow band spike buried in static. The radio silence is complete. If any artificial system exists, it would have to operate in ways indistinguishable from natural processes, or use communication methods beyond our spectrum of detection. Advanced shielding systems, if present, might also leave detectable artifacts. Natural cometary comae create complex interactions with the solar wind, forming plasma tails shaped by magnetic fields. Artificial magnetic shielding, however, would produce unusual tail structures or stable field geometries unrelated to ordinary solar wind behaviour. Observations so far reveal nothing of the sort. Both 3I Atlas and Swan R2 display precisely the tails one expects, ionised, delicate, responsive to solar wind variations, and prone to disconnection events triggered by magnetic fluctuations. Still, speculation persists, driven not by evidence but by imagination, particularly the question of timing. Why would two such different objects arrive in the same narrow window of months? If they were components of a coordinated system, their arrival could reflect planning rather than coincidence. Yet such possibilities must grapple with a fundamental constraint: the cost of interstellar travel. The energy required to send a spacecraft between stars is staggering even with advanced propulsion. Any civilization capable of doing so would presumably employ technologies invisible to our instruments or methods that do not require physical vehicles at all. The relay hypothesis is one of the more elaborate speculative models, the idea that 3I Atlas might act as a data courier, carrying compressed information gathered over an interstellar trajectory, while Swan R2, vast, bright and energetic, could serve as a processing or transmission hub. If such a system existed, the Sun itself could play a role as a natural amplifier using gravitational lensing to enhance signals aimed across great distances. Yet for gravitational lensing communication, precise alignment is essential. No such alignment has been observed, nor has any emission been detected at the wavelengths expected for directed communication beams. Artificial systems would also require thermal regulation power generation and controlled orientation processes that often produce heat signatures or brightness variations inconsistent with natural behaviour. Infrared observations with JWST reveal nothing unusual. The thermal profiles of both objects follow predictions for volatile rich bodies subjected to solar heating. The coma's evolution resembles typical sublimation not regulated heat dispersal. No flat surfaces, no repeating rotations, no anomalous glints betray the presence of machinery. Perhaps the most scientifically interesting question is not whether these objects are artificial, but whether we would even recognise artificiality if it were present. A civilization millions of years older than ours might build systems that mimic natural processes so closely that distinguishing them would require instruments far beyond those currently in use. Technology might not stand out. It might blend in quietly, elegantly, intentionally. If so, our ability to detect it would be limited not by the cosmos, but by our own conceptual horizon. For now, evidence remains firmly natural. The nickel-rich chemistry of 3I Atlas, while odd falls with implausibility for bodies formed in cold carbon, rich disks around distant stars. Swan R2's brightness reflects dust production, volatile layering, and solar wind interaction. The timing of their arrival, though uncanny, fits within statistical boundaries once selection effects such as observational bias and survey capabilities are considered. Still, the speculative frameworks have value. They sharpen our thinking about what evidence would be required to entertain extraordinary interpretations. They remind us that absence of evidence is not evidence of absence, but neither is it a license for conclusions. The cosmos remains vast, complex, and capable of surprising us in ways that are both imaginative and scientifically grounded. And perhaps that is the real function of these speculations, not to propose answers, but to expand the range of questions we dare to ask. In a sky where natural and extraordinary phenomena coexist, curiosity is not a flaw, it is a compass. When two objects cross the inner solar system at the same time, each carrying its own history, chemistry, and trajectory, the temptation to imagine a shared purpose grows naturally in the spaces where certainty fades. Human beings have always sought patterns not because the universe guarantees them, but because connection is how the mind finds order in the vastness. And in October 2025, as both 3I Atlas and Swan R2 appear in our sky like a pair of distant travellers reaching the same destination by different roads, speculation turns toward relationships cause and effect, message and reply, scout and sentinel. For some observers, the contrast between the two bodies is itself suggestive. 3 Atlas is compact, agile, and chemically peculiar. It glows with an unearthly green, carries nickel without iron, and travels in a retrograde hyperbolic sweep through the solar system. Swan R2, by contrast, is broad, luminous, and unmistakably powerful in appearance, a sprawling tail, a massive coma, a visual presence that dwarfs its interstellar companion. One resembles a probe, the other resembles a platform. The mind weaves the rest. If the first is seen as an explorer, the second becomes a depot. If Atlas gathers information, R2 becomes the one designed to receive it. In this speculative view, the smaller object arrives first, conducting reconnaissance testing, solar conditions, mapping magnetic structures, sampling particle environments. Then the larger one appears, slower, heavier, equipped to process, analyze, or transmit whatever the scout has gathered. Their timing begins to look like synchronization rather than parallel coincidence. But speculation, no matter how elegant, cannot escape the boundaries of physics. Observations reveal no signals between them, no coordinated maneuvers, no perturbations in trajectory that suggest interaction. Both follow the paths dictated by gravity, not guidance. The beauty of their convergence is narrative, not mechanical. A related theory imagines a far older system at work, an autonomous network of ancient machines scattered across the galaxy, operating without oversight from their creators. This idea does not require intelligence directing the objects now. It assumes instead a system built long ago, still functioning, still relaying, still monitoring. In such a framework, comets and icy bodies become carriers of dormant technology systems that awaken only under certain conditions, perhaps triggered by the presence of electromagnetic signatures from young civilizations. Earth's century of radio leakage becomes the spark, and in response long silent nodes drift inward once more. If that were true, the objects would not be newcomers. They would be maintenance cycles, echoes of engineering so old that even the civilizations that built them might no longer exist. Yet for all its poetry, this idea remains unanchored by evidence. No anomalous emissions emerge from 3S Atlas. No structured patterns appear in Swan R2's brightening curve. Their behaviour, while curious in detail, still sits comfortably within the envelope of natural phenomena. A darker variation imagines a predator-guardian dynamic, one object representing a threat, the other a protector. In this narrative, if Atlas were a probe with unclear intent, Swan R2 could be an intervening force, a countermeasure, a containment system, an interceptor. The scale difference between them becomes symbolic, the needle and the shield. But again, physics remains the disciplinarian. Neither object exhibits any movement inconsistent with sublimation-driven outgassing. Neither changes course, neither accelerates. Human psychology plays its own role here. We inherit myths of dual omens, twin comets, paired signs in the heavens. Our ancestors interpreted such formations as harbingers of change, the rise of kings, the fall of empires, the shifting tides of history. That symbolic heritage shapes our modern imagination even when we cloak our narratives in technological terms rather than mythic ones. The convergence of Atlas and R2 feels significant not because science demands interpretation, but because humans seek meaning in simultaneity. Even those who avoid the language of myth find it hard to ignore the timing. One object emerging from deep space, the other from the Oort cloud. One leaning inward toward perihelion, the other sweeping outward. Their paths cross not physically but temporally, like two sentences arriving at the same point in a paragraph written in different hands yet falling into rhythm. But nature is under no obligation to avoid elegance. Low probability events happen, and in a universe populated by billions of comets and an untold number of interstellar fragments, the overlap of two trajectories in a 6-week window may be surprising but not impossible. Probability allows it. Observational bias amplifies it. Human perception elevates it. If there is a shared purpose, it lies not between the comets, but between the comets and us. Their simultaneous appearance forces a deeper contemplation of origins variety and the processes that shape icy bodies across stellar systems. They give scientists a rare opportunity to compare a native comet and an interstellar wanderer under nearly identical solar conditions. They allow chemistry sublimation, ion tail dynamics, and brightness evolution to be studied side by side. In that sense, their convergence becomes a natural experiment, a coincidence that enriches scientific understanding. Perhaps the real connection is this: both visitors remind us that the solar system is open, porous, alive with movement. It receives travellers from distant stars while still releasing its own into the galaxy. We are not the centre of this motion. We are simply observers passing through one frame of a much larger film. And if some deeper meaning lies beneath it all, if the convergence hints at patterns we have not yet learned to read, then that too is part of our experience. Science is built on questions, and questions bloom when nature arranges its pieces in ways that catch our attention. Whether these objects share a mission or only a moment, they awaken the same wonder that we live in a universe capable of coincidence so striking it feels like intention. Among the more elaborate ideas inspired by the simultaneous arrival of 3i Atlas and Swan R2 is the so-called relay hypothesis, the suggestion that what we are witnessing is not coincidence, but a kind of cosmic data exchange. Not intentional in the human sense perhaps, but part of a system that could have been set in motion long before Earth formed. In this speculative picture, 3i Atlas becomes the courier, a small agile traveller carrying information gathered over a long interstellar journey. Swan R2 becomes the receiver or processor, a body large enough to conceal mechanisms capable of storing, interpreting, or transmitting whatever the courier delivers. And the Sun, with its immense gravitational and electromagnetic presence, becomes the amplifier, the energy source, or the focal point that makes the transfer possible. It is an idea with philosophical elegance even if it lacks empirical support. If one imagines a galaxy threaded with automated monitoring network systems, created not by active civilizations but by civilizations long gone, then the arrival of two objects within the same solar season begins to feel like a scheduled operation. In that framework, 3i Atlas might have been travelling for millions of years, absorbing radiation, dust, magnetic fields and chemical profiles as it passed through different regions of interstellar space. When such a courier drifts into a solar system, its destination is not the star itself, but a rendezvous point where another node, perhaps a cometary body modified long ago, awakens to receive and relay its data. The Sun, in this scenario, becomes more than a star. Its gravitational curvature could serve as a natural lens, bending and amplifying faint signals across vast distances. General relativity predicts that electromagnetic radiation passing close to a massive object is focused along a line extending outward, an effect sometimes called a gravitational telescope. Advanced civilizations might exploit this phenomenon, placing relay stations near the focal region to transmit or receive signals across hundreds or thousands of light years. If such systems existed, the solar system might be one of countless nodes scattered throughout the galaxy. And yet, for all its theoretical allure, nothing in the current observation supports this interpretation. The Sun's gravitational focus, for instance, lies far beyond Pluto, well outside the region where either comet will travel. A true relay station would not approach the inner system at all. It would remain fixed along the focal line, nor have astronomers detected any meaningful electromagnetic emissions, coherent radio patterns, or laser-like signals from either visitor. The objects remain stubbornly quiet, exhibiting only the spectra of natural sublimation. Even the chemistry that sparked speculation, the nickel without iron in 3I Atlas, falls within plausible natural pathways. Nickel-carbonyl compound space-weathering effects or formation conditions in extremely cold environments could all explain the imbalance without invoking design. Similarly, Swan R2's brightness and deep activation can be explained through solar heating, structural porosity, and conventional cometary physics. Nothing so far requires advanced systems or hidden mechanisms. Still, speculation persists because it speaks to a deeper human curiosity. The possibility that the galaxy contains not just life but intelligence, or the remnants of intelligence spread across cosmic distances. The relay hypothesis echoes questions that astronomers have asked for decades. How would a civilization communicate across thousands of light years? What technologies would survive long after their makers vanished? Could information itself be the legacy of extinct species? And if such a system existed, would we even recognize it? It is this last question that gives the relay idea its staying power. Technology vastly older than humanity's might not resemble machinery at all. It could mimic natural bodies, leverage natural processes, or hide within them. To our instruments, such systems might look like comets, because comets are efficient structures, thermally protective, abundant, mobile, and chemically diverse. An engineered system that uses sublimation, or solar heating for energy, would resemble a natural comet in every measurable way except in its purpose. But purpose is the one thing science cannot detect. It can measure motion chemistry, temperature, and radiation. It can reconstruct orbits and infer origin regions, but it cannot determine intent, not without evidence beyond physical behaviour. And so the relay hypothesis remains speculation, in the purest sense imaginative, thought-provoking, and scientifically unconfirmed. It expands the landscape of possibility, even as data keeps us anchored in conventional explanations. What it truly reveals is not a cosmic network, but the human desire to find meaning in convergence, to imagine that when two wanderers arrive together, they are part of something larger. Perhaps in a way they are, not because they share a mission, but because they offer us a rare parallel, two different histories illuminated by the same star. Two icy bodies behaving according to physical laws, yet stirring questions that reach far beyond physics. Whether natural or extraordinary, their presence invites us to wonder, what else may drift between stars carrying stories we do not yet know how to read? The sun burns with a ferocity so constant, we often forget that it is in cosmic terms a giant machine, one that converts 4 million tons of mass into radiant energy every second. Its light sustains life, drives weather sculpts, planetary atmospheres, and fills the solar system with a continual stream of plasma and charged particles. We think of the sun as the centre of our world, yet in a universe of innumerable stars it is simply another furnace among billions. And so when two luminous visitors approach it in the same season, one from interstellar space, the other from the deep roots of our own system, a new line of speculation emerges. What if stars, including our sun, are not just sources of heat and gravity, but resources? The harvest scenario is among the most imaginative frameworks proposed in response to the October convergence of 3I Atlas and Swan R2. It suggests that comets might be more than drifting ice. They could serve as tools for extracting energy or rare materials from the stellar environments they pass through. The concept is not entirely foreign. Humanity itself has envisioned Dyson spheres, stellar energy collectors, and exotic propulsion systems built on manipulating solar wind. If advanced civilizations exist, their engineering might operate on scales we cannot yet conceive, and comets with their porous bodies and vast comae could provide natural platforms for converting solar radiation into usable power. Swan R2, with its immense sweeping tail and extraordinary output of dust and gas, becomes an easy metaphor for such imaginings. Its expanding cloud interacts with solar wind in ways that, to an imaginative observer, resemble the intake structures of a colossal engine. The dust tail curves softly away from the sun, driven by radiation pressure. The ion tail stretches in the opposite direction, rigid and straight-shaped by electromagnetic forces. These natural structures mimic the basic principles behind solar sails, plasma collectors, and hypothetical particle harvesting devices. The harvest scenario proposes that a sufficiently advanced system could use these natural flows for extraction. Solar wind carries helium-3, exotic isotopes, and charged particles that might be valuable to civilizations beyond our comprehension. In this speculative lens, a large comet like Swan R2 would not simply pass through the solar wind. It would feed upon it using magnetic funnels disguised within its coma to concentrate and process rare materials. The sun's outer atmosphere, filled with bizarre states of plasma and exotic particle distributions, could serve as a resource field far richer than any planetary surface. Such concepts push against the limits of known physics, yet remain within the realm of the imaginable. Micro-wormhole networks stabilized by strong magnetic fields. For instance, are theoretical constructs that require conditions found only near stars or neutron remnants. If any civilization had mastered such infrastructure, it might conduct harvesting operations not through spacecraft in the conventional sense, but through modified natural bodies comets, engineered to withstand extreme environments and carry exotic materials away. 3i Hor Atlas, smaller and more compact, would fit into this story as a surveyor. It could scout the sun's magnetic conditions, assess solar wind density, or map plasma structures before the larger collector arrived. Its peculiar chemistry, nickel without iron carbon dioxide dominant cyanogen signatures, could in speculative interpretations be read as the byproducts of engineered systems. But science grounded in data rather than metaphor finds natural explanations for each of these anomalies. The chemistry, unusual but not unprecedented, fits comfortably within what might arise in the cold outskirts of another star. Yet the harvest scenario retains its appeal because of the sun itself. The sun is a natural engine operating at unimaginable scales. Even without invoking technology, its environment produces phenomena so strange that they defy intuitive understanding. Plasma waves taller than Earth magnetic loops that collapse with the energy of billions of bombs, temperature inversions that heat the corona to millions of degrees while the surface remains cooler. To a mind steeped in astrophysics, the idea that civilizations might harness such effects does not sound impossible. It sounds ambitious. Still, the observational evidence refuses to cooperate with such theories. No anomalous acceleration signal artificial station keeping, no coherent electromagnetic emissions suggest data transfer or energy processing. The tails of both objects behave precisely as physics predicts: no unnatural kinks, no persistent alignments, no deviations from the solar wind's influence. Infrared data reveals no unusual heat signatures. Radar returns that faint match those expected from porous, icy bodies rather than metallic structures. Every measurable quantity remains within natural bounds. If Swan R2 or 3i Atlas were harvesting solar energy, we would expect to see behaviours inconsistent with sublimation-driven outgassing, stationary hovering, repeated braking-controlled orientation. Instead, they move through space exactly as comets do, pushed by sunlight, tugged by gravity, shaped by thermal gradients. Their tails respond to magnetic fluctuations in ways that mimic dozens of comets studied over the last century. And yet the harvest scenario persists not because it is probable, but because it is evocative. It reflects the human desire to imagine purpose in celestial motion. It mirrors our own aspirations to reach the stars, to build technologies capable of harnessing the cosmos. It expresses a simple truth that the boundary between natural wonder and imagined design is thin, especially when the universe presents us with coincidences so striking they resemble choreography. Ultimately, the value of such speculation lies not in its likelihood, but in its capacity to expand our conceptual horizons. It asks us to consider what advanced civilizations might do with physics we only dimly understand. It challenges us to imagine the sun not just as a sphere of burning plasma, but as a member of a larger ecology of stellar processes, possibly even a resource in a galactic economy we cannot yet detect. Perhaps the true harvest is not energy gathered from the sun, but the questions gathered by us. These visitors, interstellar and native green and brilliant, remind us that the solar system is not closed. It is porous, dynamic, receptive. And for a brief moment in 2025, two icy wanderers have drawn our attention back to the furnace that sustains every atom of life on Earth. And now, traveller, our journey comes to a gentle close. We have followed two wandering lights into the October dark, watching their paths cross like quiet thoughts in a vast celestial mind. As they slip into silence, we are reminded that the universe speaks in long, patient sentences, some we understand, most still beyond us. Yet the wonder they stir remains our own. A reminder that even on this small world we belong to something ancient and alive. Tonight, observer, we listen together. When December's light returns them, we may learn more or simply learn to wait. Rest well now. Stay curious. The universe will keep watch.